Okay, good morning to all of you. Whether the slide is visible? Yes, anyone please respond.
Yes, sir.
Okay. Yesterday we have discussed that there are two types of white box testing techniques. One, coverage based testing. Two, fault based testing. In coverage based testing, we have to execute or cover, or we will design test cases in such a way that some elements of the program will be covered, such as each statement will be covered, or each branch will be covered, or each path will be covered. Those are known as coverage based testing techniques. Examples are statement coverage, branch coverage, condition coverage, path coverage, etc. The other category is fault based testing, where we will inject or introduce some known faults, and with the help of those known faults, or by seeding those known faults, we will try to detect some other remaining or some other hidden faults. That is fault based testing. The example is mutation testing, which we have discussed in the last class. So today we'll discuss about the coverage based testing techniques. Okay. So today we'll discuss about the coverage based testing techniques such as statement coverage, branch coverage, condition coverage, MCDC coverage. Path coverage we will discuss in next class. Okay. So let's start with the statement coverage based testing. What do you mean by statement coverage technique? Or in statement coverage methodology, what do we do? In statement coverage methodology, we have to design test cases so that every statement in the program is executed at least once. We have to design the test cases in such a way that each and every statement present in the program, they have to be executed at least once. That is the principal idea behind statement coverage based testing. The principal idea behind statement coverage testing is that unless a statement is executed, we have no way of knowing if an error exists in that statement or not. And if there are some 10 statements, if you are not executing each and every statement, how can say that the statement is error free or correct? So in order to know whether a statement contains some errors or not, we have to execute that statement. This is the principal idea behind statement coverage based testing. So the principal idea behind statement coverage testing, unless a statement is executed, unless we execute a statement, then we have no way of knowing, we cannot know, we do not know if an error exists in that particular statement or not. So the objective is we will design the test case in such a way that each and every statement of the program will be executed at least once. But please remember that observing that a statement behaves properly for one input value, it does not give guarantee that it will behave correctly for all input values. It's not sure that you are saying that you have designed the test case in such a way that a statement is behaving properly, correctly for one input value. It does not give guarantee that it will behave correctly for all the input values. It is not guaranteed. Still, we'll see. Still, statement coverage based testing is useful. We'll try to execute, we try to cover each and every statement so that maximum of the faults we can detect. How can measure the efficiency of the statement based testing? The efficiency of the statement based testing can be measured using the following metric. Here we call it as coverage measurement. The coverage measurement is equal to, it is defined as, or it is equal to number of the executed statements divided by the total number of statements. And if you want to measure in percentage, multiply by 100, and your objective should be achieving 100% statement coverage. So each and every statement should be covered at least once. The rationale behind statement coverage based testing is that a fault in a statement can only be revealed, it can only be detected by executing the faulty statement itself. So unless you will execute that statement, you cannot detect the fault. So a fault in a statement can only be revealed, it can be only be detected by executing the faulty statement. Okay. This is the rationale behind statement testing. Let's take a small example and we will try to generate test cases using statement coverage based testing. This is a simple function I have written. Anybody else can look at the program and say what does it represent? This small program, while x is not equal to y, and then if x is greater than y, then it is x is equal to x minus y, else y is equal to y minus x. Return the value of x. Anybody else can say this very popular program represents what? Yes, it represents Euclid's GCD algorithm. Those who have known how to compute the GCD, Euclid has developed an algorithm for GCD. So this is known as Euclid's GCD algorithm. So very simple code. Now I want to generate test cases using statement coverage based testing. What is the objective? I should design test cases in such a way that each and every statement will be executed once. So here test case means what? What is the input and what is the expected output? So normally we have to consider the input. We will design the input in such a way that each and every statement will be executed at least once. So how many inputs are here? Two inputs, x and y. So let us choose, let us select the values of x and y in such a way that each and every statement in this function will be executed at least once. This is what is meant by statement coverage based testing. Let's try. You can see here there are first is while x not equal to y. That means I will first choose in such a way that x should not be equal to y. So that what will happen? This if part will be executed, isn't it? And you can say when if there are actually two conditions that x is greater than y, then the then part will be executed. If x is not greater than y, that is if x is less than y, then the else part will be executed. So how I will choose the values? First I will choose x is not equal to y, so that this will be executed. And second, what you see, then while x is equal to y, when x is equal to y, what will happen? It will come out of the while loop and it will come to return x. I also require return statement should be executed. So another value I will choose what? X is equal to y. Please see how I am designing. First condition, x should not be equal to y. If this will be satisfied, then the loop will be executed. So let us first take x not equal to y. Say 2, x is 2, y is equal to 3. Then I have to choose another value, x equal to y. When x will be equal to y, then return statement will be executed. So another case I have to take x equal to y. Then another case what I will take, x not equal, x is greater than y. I will choose the value of x in such a way that x is greater than y, so that x is equal to x minus y. Else y is equal to y minus x. So let's design how the test cases we can design. So I have chosen the values in such a way. For the first case, while loop, once x not equal to y and once x equal to y. Two possible sets I have designed here. X is equal to 3, y is equal to 3. Then another case, x is not equal to y, that is x equal to 4, y is equal to 3. Then for the if statement, I have to choose similar two sets values. Once x greater than y, another x less than y. So already x is equal to 4, y is equal to 3. Already it is greater than y. X is greater than y. So no need to choose another one. Another case, x is less than y. So x is equal to 3, y is equal to 4. So x is less than y. So if I choose these three sets of values for x and y, then all statements in the program are executed at least once. You can see with these three values, I can execute all the statements. All the statements present in the small program are executed at least once. Okay, this is how you can design test cases for this Euclid's GCD algorithm using statement coverage based testing. Okay, next we will go for the next coverage, that is the branch coverage based testing. So here test cases are designed in such a way that different branch conditions, they are given true and false values in front. That means what? In branch coverage testing, we should design test cases in such a way that each and every branch will be executed at least once. So each and every branch will be executed once means if there is a if statement, so you have to give the value in such a way that once you have to give the true value, next you have to give the false value. In that way, you can do this thing. Okay. So, so in this way, branch coverage can be achieved. We have to design test cases in such a way that the different branch conditions, maybe the then part and the else part, they are given true value once and false values next, false values in top. Please remember that branch coverage based testing, it guarantees statement coverage based testing. So what do you mean by this? Branch coverage based testing guarantees statement coverage based testing. It means that when what the branch coverage is, or when what in if your test cases, using your test cases, you are achieving branch coverage, this guarantees that automatically statement coverage is achieved. If you are achieving branch coverage by a set of test cases, then it is guaranteed that automatically statement coverage will be achieved. In other words, I can say that a branch coverage testing is a stronger testing technique compared to the statement coverage based testing. So what do you mean by stronger testing? We'll say first, stronger testing means the test cases of the stronger testing means it is a testing technique where the test cases are a superset of a weaker testing. The test cases of a stronger testing are a superset of weaker testing. What does it mean technically? A stronger testing covers at least all the elements of the at least all the elements of the program covered by a weaker testing. Okay, a stronger testing covers at least all the elements. Okay, covered by a weaker testing. If the weaker testing covering 5 statements, then a stronger testing, I have already told you, branch testing is a stronger testing. It will must cover those 5 statements plus some extra statements it may cover. That is what it means by stronger testing. So here, first, if a weaker testing covers n number of statements, a branch or elements, a stronger testing will cover those n number of elements, maybe those n number of statements plus some extra, some more. That is what is meant by stronger testing. I have given a typical what example through a figure. So suppose this purple color represents what your weaker testing, and this what blue color represents what this or green color represents this weaker test, stronger testing. You can see that this weaker testing is a subset of the stronger testing, or the stronger testing is a superset of the what weaker testing. That means the test cases present in a stronger testing is a superset of the test cases of the weaker testing. What do you mean by complementary testing? Some of the test cases are common in both of them. In the green case as well as in this what gray case, see some of the elements are common. So that's why I say that these two testing techniques, the green one and the purple, this gray one, they are complementary to each other. Okay. So now we'll explain this branch coverage testing by taking the same example. Again, I am taking the Euclid's DCD algorithm and I am using branch coverage. You can see how many branches are there in this program. Please look at 2 branches. One is at the while line, because here x can be equal to y, another is x is not equal to y, and another branch is present at line number 2. That is if, because if is this x greater than y, there are 2 possibilities. X may be greater than y, x may be less than y. So there are 2 branches we have taken. What we have to do for each branch, we have to first give the true value, next the false value. So for the while, I have to first choose x is not equal to y, then I have to choose x equal to y. For the second branch, first I have to choose the value of x and y in such a way that x is greater than y, and next I have to choose the value in such a way that x should be less than y. So what are the test cases? I have designed the test case like this. This is for the while case. A first pair x is equal to y, second pair x is not equal to y. Then the third pair is x is greater than for the if clause. For the if clause, one is x is greater than y, next is x is less than y. So I have chosen the values in such a way that in the third pair x is greater than y, and in the fourth pair x is less than y. You can see that this is a superset of the statement coverage testing. Some test cases are extra, and you can see that the statement coverage based testing, it is a subset of the previous testing. This is the statement coverage based testing. Only 3 test cases are there, 3 pairs of test cases, and in branch coverage testing we have added one more, because here in the statement coverage I have chosen the same thing, that x is equal to 4, y is equal to 3. I have treated both in the for the while clause as well as for the if clause. But here explicitly I am writing one value, one pair value, or the while one branch, that is the while branch explicitly wants true, next time false. Similarly, the if clause once true, next time false. So there are 4 elements you can see, but in statement coverage we have taken 3. So now the test cases in the branch coverage, here it is 4. It is a superset of the statement coverage, the test cases present in the statement coverage testing. So it is a stronger testing than the this statement coverage testing. It will detect. It is expected that branch coverage testing may detect few errors extra than this the statement coverage testing. So all the what statements will be covered in statement coverage testing, those are must. They must be covered in branch coverage testing. It may be that in branch coverage testing some more elements or some more statements may be covered. This is stronger testing than the what statement coverage testing. How can measure its adequacy? How can measure its efficiency? Again, we can use the metric, the following metric. Adequacy criterion, each branch, that means if you represent in the graph, the branch will be represented at the edge and the statement will be represented at the nodes. So each branch or edge in the control flow graph must be executed at least once, isn't it? Branch coverage testing means each branch or each edge in the corresponding control flow graph must be executed at least once. How can measure the coverage? So coverage will be equal to the number of executed branches divided by the total number of branches into 200. In that way you can get the coverage for branch testing. Okay, so the coverage for branch testing is defined as number of executed branches by the total number of branches. So now quickly let's see statement versus branch testing. So in in branch testing, traversing we are traversing all the edges of the graph. That means all the branches. Traversing all edges of the graph automatically causes all nodes to be visited. So automatically all nodes, here nodes represent the statements. So traversing all edges of a graph causes all nodes to be visited. So that's why branch coverage testing is a stronger testing than statement coverage testing. Traversing all edges of a graph causes all nodes of the all nodes to be visited. So the test suits that satisfy the branch adequacy criterion for a given program P also satisfy the statement coverage criterion for the same program P, because when you are traversing all edges of a graph, in a graph edges will represent the branches and nodes will represent the statements. So if you are traversing all edges of a graph, automatically it causes all nodes to be visited. So the test cases that satisfy the branch adequacy criterion for a given program P also satisfy the statement adequacy criterion for same program P. Hence, branch coverage testing is a statement coverage testing. In the examination, there might be a 2-mark or 3-mark question. Prove that branch stronger than statement coverage based testing. You can give this proof. But please remember, I have told that branch coverage testing is a stronger testing than statement coverage testing. But the reverse is true. It's not true. The converse is not true. That is, statement coverage test when branch adequate or edge adequate. That means in some test cases, then automatically statement coverage testing is accomplished. But if a set of test cases they accomplish, they achieve statement coverage, it does not guarantee that they will achieve branch coverage. So a statement adequate for the test suite may not be branch adequate, but a branch adequate test suite, it must be statement adequate. Okay. Now we'll go to the next coverage, that is the condition coverage. So similar strategy. So in this testing technique, the test cases are designed in such a way that each component of a composite conditional expression is given both true and false values. Okay, each component of a composite conditional expression. So you know that conditional expression A and B or C and or D or and E, like that. So this is a composite conditional expression. So the test cases in condition coverage testing are designed in such a way that each component of a composite conditional expression, it is given both true value and false value. Once the condition will be given to true value, next time the condition will be given false value. Okay. So if you will compare again branch and condition coverage based testing techniques, so then you can see that condition testing is a stronger testing than branch coverage testing. That means if the test cases achieve condition coverage, that means it is guaranteed that they will achieve branch coverage. And previously we know branch coverage testing is a stronger testing than statement coverage testing. Now you can apply principle of transitivity. So what you will get, that condition coverage testing is also than statement coverage testing by applying principle of transitivity. So branch testing is the simplest condition testing strategy. If you generalize, in other words, you can say that branch testing is the simplest condition testing strategy. The compound conditions appearing in the different branch statements are given true and false value. So in this testing, the compound conditions which are appearing in the different branch statements, they are given true and false values. One time true, next time you have to give false value to the compound conditions. So let's see MCC or multiple condition coverage. In multiple condition coverage, it reports whether every possible combination of Boolean sub-expression occurs. So each and every possible combination of the Boolean sub-expression that has to be occurred, that has to be satisfied. The test cases required for full multiple condition coverage of a condition are essentially given by the logical operator truth table for the condition. You have to construct the truth table, then you can generate test cases for full multiple condition coverage. We'll take a small example. Before going to example, let's conclude that in multiple condition coverage, the test cases are designed in such a way that each component of a composite conditional expression, it is given both true and false values. First you may give true value, next false value. Or first and give false value, next you have to give true value to the to each component of a composite conditional expression. We'll take a small example, suppose. So let's consider the conditional expression C1 and C2 or C3. So here you can see there are three conditions C1, C2, C3. Each of the conditions C1, C2 and C3, they are exercised at least once. That means you have to design test cases in such a way that each and every condition present in this conditional expression, that is C1, C2 and C3, they have to be executed at least once. How? You have to give C1 to once true, then false. Maybe C2 then once true, next false. Give C3, design test case in such a way that C3 first it will be true, next it will be false. Each of the conditions C1, C2 and C3, they are exercised at least once. That is, they are given true and false values alternatively. Let us quickly take a small example. Suppose there is a small program. In this small program, two conditions are there. If A and B, then function 1 will be invoked, else function 2. Then if C or D, then function 3 will be invoked or function 4 will be invoked. So now let's see, we'll design test cases for condition 1. In condition 1, how many individual conditions are there? 2. How I can construct the, I have already told you here that the test cases which are required for a full multiple condition coverage of a condition, how they are constructed. The test cases required for full multiple condition coverage of a condition are essentially given by the logical operator truth table for the condition. So we have to construct the truth table. So now here are two conditions A and B. They are connected by the AND operator. So how the truth table will look like this: A true, B true, A true, B false, A false, B true, A false, B false. So all the I am discussing multiple condition coverage. So all the condition coverage you have to take, all the possible combinations. So since there are two variables, I will get what 4 number of combinations. So these will be the test cases. Similarly for condition 2, it is C and D. I have to design, I have to choose the values of C and D in such a way that all the possible combinations will be satisfied. So what are the possible combinations? Again, C true, D true, C true, D false, C false, D true, and C false, D false. In this way, we can design test cases in such a way that each condition is executed at least once. the components in the conditional expression, each component is executed at least once, and it is all the possibilities, all the possible combinations are considered here. That means once true, next false we have to give. First we have given to value of A true, then B false. Then what we are giving, first both of them are true, then A true, B false, then A false, B true, then A false, B false. Like this, you can construct the truth table, and these will be the test cases for multiple condition coverage. Okay. So how you can measure the efficiency? Here we have to use an adequacy criterion. The adequacy criterion like this: each basic condition must be executed at least once. The adequacy criterion for MCC is that each and every basic condition must be executed at least once. The coverage can be defined as the number of truth values taken by all the basic conditions divided by 2 into the total number of basic conditions. In this way, you can find out the adequacy criterion for MCC. Okay. So if we'll compare branch testing versus MCC, I have already told you. Multiple condition coverage testing is the stronger testing than branch testing, because we are considering what each and every possible combination. And I have already told you branch testing is stronger testing than statement coverage based testing. So I can conclude that by applying principle of transitivity, multiple condition coverage testing is a stronger testing than statement coverage based testing. Okay. Now let's see what is the problem of MCC and why we should need a feasible testing technique. Let us consider a Boolean expression having n number of components, C1 and C2 or C3 like that, and Cn like that. There are n number of components. For achieving condition coverage, how many test cases we require? We have to construct the truth table. You know, if there are n number of components, you have to construct the truth table where 2 to the power n number of rows should be there. You take, for example, simple A and B or C, 3 conditions. How many rows will be there? 2 to the power 8 number of test cases. So if you will consider a Boolean expression having n components, for condition coverage we require at least 2 to the power n number of test cases. Okay, and you can see how much big this is, like this. So for A or B and C, in order to test this using multiple condition coverage, I have to consider all the possibilities, all the permutations. So 8 number of test cases are required. Please imagine if there are 10 number of components, A and B, or A or B and C or D and E, like this, 10 number of individual components. Then how many number of test cases have to design? 2 to the power 10, that is 1024, such a big number. So that is the drawback of MCC. The number of test cases grows exponentially. So that's why condition coverage based testing technique is practical only if n, that is the number of component conditions, is small. If it is very high, it is quite difficult, very difficult to design test cases for that. So for example, if n is equal to 10, that is 10 number of individual components are there, then we have to design 2 to the 10, that is 1024 number of test cases, such a bigger number. So as n increases, the number of test cases grows exponentially. So condition coverage testing technique is practical only if n, that is the number of component conditions, is small. That's why there is a need. Okay, so that's why there is a need of a feasible testing technique. We have to develop another feasible testing technique where the number of test cases will not grow exponentially. They can be managed easily. Let's see what is that method. I have already told you. So it is exponential in the number of basic conditions. If the basic conditions such as ABC increases, then the number of test cases grows exponentially. There is exponential growth in the number of basic conditions. That's why many industries, many people, they do not use MCC. Let's see what is the feasible solution. So there is a need to develop a feasible solution. The solution is MCDC, modified condition decision coverage. Okay, so what is the motivation? Why in multiple condition coverage the size of the test suite grows? Because we are considering each and every possible combinations of the components. That's why the size is growing exponentially, maybe of the order of 2 to the power n. So our objective is, if we can, we will not consider each and every possible combination. We will only consider some important combinations. Then perhaps the number of test cases can be reduced. So motivation is that we have to effectively test only the important combinations of the conditions, not all the possible combinations, without exponential blown up in test suite size. So without making exponential blown up in the test suite size, without exponential blown up in test suite size, if we can test only the important cases, then we can achieve what the coverage can be achieved, and the size of the test cases will also be less. So what do you mean by important? Important combination means each basic condition is shown to independently affect the outcome of each decision. So how many basic conditions? You have to show them they independently affect the whole outcome, the total outcome of the each decision, without depending on the other conditions. If A, B, C are there, A and B or C, A can itself change the whole outcome without depending upon the values of B and C. This is what is known as independently affecting. So important combination means each basic condition is shown to independently affect the outcome of each decision. So this condition, this MCDC requires what? This MCDC testing requires for each basic condition C, there should be 2 test cases. Okay, for each basic condition C, there should be 2 test cases. One, values of all evaluated conditions except C are the same. Okay, so if for each basic condition C, 2 test cases are required, the values of all the evaluated conditions except the condition C are the same, then the compound condition as a whole, the compound condition as a whole evaluates to true for one value and false for the other value. We'll explain all those things maybe through a small example. So what is MCDC? Let us summarize. I have already told you it stands for modified condition decision coverage. It is also a kind of predicate coverage technique, just like as last class, before few slides we have seen branch coverage, condition coverage. So MCDC is also a kind of predicate coverage technique. So in this technique, 2 important things you'll see, 2 important terms, the condition and the decision. Here in condition, so condition means the leaf label Boolean expression. So condition means it represents the leaf label Boolean expression. Boolean expression you already know, and if you can represent as a tree structure this Boolean expression, the leaf label Boolean expressions will represent the conditions, and the decision what they will do, the decision will control the program flow. The program flow will be controlled by the decision. What is the main idea behind MCDC testing? The main idea behind MCDC testing is that each condition must be shown to independently affect the outcome of a decision. Just remember in MCC what we have done, that we have to design test cases so that each and every condition will be given once true value, next false value. But here the main idea is that each condition present in the compound statement must be shown to independently affect the outcome of a decision. How many combinations, how many components may be there? Each condition must be shown to independently affect the outcome of a decision without taking the help of the other conditions. That is, the outcome of a decision, it changes as a result of changing a single condition. If we just, there are 3 conditions A and B or C, A can change depending on B and C. If A is true, if the whole outcome is true, when A becomes false, without depending upon the value of B and C, again the whole outcome becomes false. This we say that the outcome of a decision, it changes as a result of changing a single condition without taking the help of the other conditions. I am giving a small analogy for MCDC testing. So Lucy is asking what's modified condition decision coverage testing. Then Philippa is giving giving an analogy. Here is an analogy. So you might have known that. So imagine that a light is controlled by 3 switches. You might have seen in bathrooms, etc. Joint these switches should be there for one bulb. So here a bulb is connected through 3 switches. In MCDC testing, we need to show that each light switch can independently turn the light on or off. Even if there are 3 switches, any one switch you put, it can turn off the bulb or turn on the bulb without taking the help of the other 2 switches. That's what I'm saying here. In MCDC testing, we need to show that each light switch, it can independently turn the light on or off without taking the help of the other 2 switches. How does that apply to software here, or how does it apply to software testing here? Here the light corresponds to decision. So this light it corresponds to decision. And what do the switches represent? The switches, they correspond to the condition. So here the switches will be the conditions and the light will be the decision. So if any of the switch independently make the light turn or off, turn on or off, then we say that MCDC testing is similar to that. The light corresponds to the decision and the switches, they correspond to the condition. So now let's a little bit see about condition coverage. Then we'll go for what is this MCDC. Here every condition in the decision has taken all possible outcomes at least once. If you go to the normal condition coverage testing or the multiple condition coverage testing, how it will work? So here every condition in the decision has taken all possible outcomes at least once. What are the possible outcomes? You have to give the value true to once and next false. You can see here there are 3 components. First you have to give A true, then B false. Next time B true, B false. Next you have to give C the value true, next false, like this. So here in this way every condition in the decision has taken all possible outcomes at least once. This is happening where? In a condition coverage or multiple condition coverage. But let's see how does it differ from MCDC. In MCDC what is happening, let's see. But in MCDC we are not doing that. We are not giving all possible values to all the conditions. What here you do? Every condition in the decision will try that it is independently affecting the decision's outcome. So that means we will change only one condition at a time, keeping the other 2 conditions fixed. So here please see what I have done. First I am giving the value of A to true. Whatever the value of B and C may be, they will be fixed. I will see the output. Then what I will do, the value of B and C fixed, we will see the outcome. If I try to see fixed, then we say that yes, this is an important combination and this affects, that means the value of A is able to independently change the status, the value of the whole compound condition. So here what we are doing, please change the value of each condition, only one at a time, individually, while keeping all other conditions constant. First you give A true, whatever value of B you have given, keep it, see the outcome. Then change the value from A to true to false, keeping the value of B and C fixed, see what is the outcome. If there is a change in the whole outcome, then you say that yes, this is an important combination and this is a MCDC test case. Similarly, next time what you do, keep A and C fixed, give value of B to true, next to false, see the outcome, whether there is a change in outcome or not. Next time what you do, keep the value of A and B fixed. What you do, first give C to true, observe the output, then they give the value of false to C, observe the output. If there is a change in the output, then you say that yes, this is an important combination. The value, the whole output is changing. We say that this is MCDC test case. In this way, you can design the MCDC test cases. So I am explaining a small example now for MCDC testing. Please try to understand carefully. This will help you. So I have taken a compound expression A or B and C or D and E. So if I will go for this normal testing or condition coverage testing or multiple condition coverage testing, how many test cases I have to design? 2 to the power 5. That is 32 number of test cases I have to design, because there are 5 conditions A, B, C, D, E. 2 to the power 5, 32. So now let us apply MCDC. Let's see how many test cases we require. What is MCDC? I have already told you. So first change, what you do? First give the value A to true. Whatever value B, C, D you are giving, keep it fixed. Next you give value of A to false. So if the whole output is changing, we say that yes, this is a valid pair for MCDC test case. In this way, I have to do for all. Next time what I will do? I will keep A, C, D, E fixed, changing the value of B from true to false. Observe the output. If there is a change, then this is a valid test case, MCDC test case. Next, I have to change the value of C from true to false. Keeping A, B, D, similar. And last time I have to change the value of E from true to false by fixing the values of A, B, and C, D. What fixed? Okay. So in this way, let's design the MCDC test cases. So I am saying that first, let us do the MCC. So I have already told you, you have to design 32 number of test cases, because there are 5, 2 to the 5, 32. Now let's see what I have told. First, let's go for A. Let us keep the value of A is true, and the B value, since it is OR, you can give anything else. So this double dash means don't care condition. Whatever you may give to B, what I will get here, A is true means this pair will be A or B is true. Then and I have given C value to true. So what you will get here now? Again true, because A or B is true, C is true. So this they are connected through ampersand, and so this will be true. And next, whatever may be the value of D, because this is OR operation, even if it be true or false, I do not worry. This portion, left hand portion, will be what? Again true. And E value I have taken true. So what will it whole outcome? Whole outcome is true. Now what we will do? Keeping the value of B, C, D fixed, what I will change do? I will try to change the value of A. Initially I have taken true. Now I will take which one value? False. Keeping the value of B, C, D fixed. So now let's do. Please come to the last test case. Value of A is now changed from where? True to false. All others should remain fixed. Fixed on the, let's see. B is don't care. Don't care means anything else you can take. So I have taken false. C is true. I have taken here don't care. That means it can be true or false. D is don't care. I have taken false. E is true. I have taken don't care. Anything else you take. So what is the outcome here? You see. Now it is becoming false. You take any one. A is false. B is false. So false, false is false. And C, whatever it may be true or false, don't worry. This portion will be false. And D I have taken false. So false or false is false. And E value, whatever may be, true or false, what I will get? The whole outcome is false. So now, what you will say in this case? This is an important combination, because by changing the value of A from true to false, by keeping the values of B, C, D, E, I am able to change outcome here, true to false. Similarly, repeat now for B. Keep the values of A, C, D, and E fixed. Change the value from true to false. See whether there is a change in the outcome. If there is a change in the outcome, that is a valid test case, MCDC test case. Let's do. Now test case number 2. So I have given value of B to true. Whatever other value I have given, I am keeping fixed. A value is false, because false or true. Now this will be true. Then and C again I am taking true here. C. So true and true is true. Whatever value of D I do not worry. So that's why I don't care. That will be, so this portion will be true and E value is true. So what is the final outcome? True. Now what I will do? The values of A, C, D will remain fixed. What I will change? The value of B I am changing. Initially value of B is true. Now I am, please come to last one. The value of B, now I am changing from true to false. Keeping all other values fixed. See how fixed? A is false. Here also is false. 2 and 13. Please check 2 and 13. B I have changed. C it is true. I have made it don't care. No problem. D is don't care. And I have used false. No problem. E is true. And here it is 13. It is don't care. No problem. But what is the final outcome? Final outcome is also false. That means there is a, when B was true, the whole outcome was true. Now I have changed the values of what? A, C, D, E. Only value of B is changing from true to false, but there is a change in the whole outcome. That is false. That means this is a valid pair and this is a valid test case. Similarly, you can repeat for C, D and E. Okay. So if you see, these many test cases are sufficient. How many we are getting? 1, 2, 3, 4, 5, 6. 6 test cases are sufficient to test this conditional expression using MCDC testing. Had it been the condition testing or multiple condition coverage testing, how many test cases you would have required? 2 to the power 5, that is 32. Now you see the number of test cases is successfully reduced to how many? 32 to 6. That is the advantage of MCDC. It is not growing exponentially. Okay. So here, what these underlying values represent? These underlying values, they independently affect the output of the decision. So here 2 means its counterpart is 33. 1 and 13. They are underlined. So they change the whole outcome. Similarly, B value 2 in 2, test case number 2, and B value is false in test case number 13. That means 2 and 13. These test cases 2 and 13, they independently change the outcome from true to false. Okay. So one conclusion I can say that for MCC we require 2 to the power n number of test cases, but in MCDC test cases we require only n plus 1 number of test cases for n basic conditions. This is linear in size. So test cases, the size of the test suite will not grow exponentially. So why you are reading this MCDC? These MCDC test cases nowadays are very much required by the RTCA DO 178B standard, especially when you are designing safety critical systems. You have to thoroughly test your software. I have given the example of Ariane 5 software rocket, the software for that. So any safety critical system nowadays, the government says that you have to achieve MCDC testing. So you have to thoroughly test this. So that standard we call RTCA DO 178B standard. So nowadays MCDC is required. It is mandatory by the RTCA DO 178B standard. Okay, this is how this MCDC testing is occurring. Now let us quickly take a small example. Before going to that small example, we'll take the comments on MCDC. Then we'll take a small example. So basically, MCDC is a basic condition coverage because it stands for modified condition coverage. So first of all, condition coverage we are achieving. So MCDC is a basic condition coverage and branch coverage. D means decision means branch. So MCDC is basic condition coverage and branch coverage. But one thing extra. What is that extra? Plus one additional condition M is there. M stands for modified. So MCDC is basically a basic condition coverage, which we have already seen. It is a basic branch coverage. Branch coverage already we have seen. D means decision means branch. But here one thing is extra. What is that extra? Plus one additional condition M. M stands for modified. What is this additional condition says? It says that every condition must independently affect the decision's output. Okay. So each and every condition must independently affect the decision's output. This testing MCDC is subsumed by compound conditions and subsumes all other criteria discussed so far. That means it is the strongest testing among all other testing techniques we have seen, such as statement coverage, branch coverage, decision coverage, etc. But it is little bit weaker than the MCC, multiple condition coverage, because there we require many test cases 2 to the 32 to the n. Obviously, this will be much more strong then, but it will take a huge amount of time to design. So that's why people are preferring MCDC. This is the second strongest criteria. First strongest is MCC, multiple condition coverage. This is the strongest criteria. This is the second strongest criteria. It is subsumed by the compound conditions or MCC technique, and it is subsumed all other criteria discussed so far. That means it is stronger than statement coverage and branch coverage testing, but weaker than MCC, multiple condition coverage based testing. So since here, even if little bit we are sacrificing the coverage, but here the number of test cases is very less, there is a good balance of thoroughness and the test size, and therefore it is widely used in software industries nowadays. So please have a look into MCDC testing. Please read yourself in detail. Now we'll take quickly two examples. I have taken the first example, only two compound conditions A and B. What are the steps to generate MCDC test cases? First step, create a truth table for the conditions. Okay, first step is create the truth table. So here for A and B, I can easily construct the truth table. There are two components. So obviously, I should get a 2 by 2, 4 number of rows. So 4 number of rows I have shown here. Then what you do? Extend the truth table so that it indicated which test cases can be used to show the independence of each condition. Then what you do? You extend the truth table. Okay. Then you extend this first original truth table so that it indicated which test cases can be used to show the independence of each condition. So let's now try to do. So we have to see that which test cases can be used to show the independence of each condition. Let's say first one, A and B. You can see by keeping A value true, B value true, the whole result is A and B. You can see it is true. Now I will see keeping keeping B value fixed. If I change the value of A from true to false, is there any change? Let's see. So now I can check where A value is changed. 3 and 4. Let us check test case number 3. So now B value is fixed, true and true. Only A is changed from true to false. What is the net outcome? The whole outcome. Yes, there is a change in the whole outcome. That is now whole outcome is changing from true to false. What does it mean? That test case number 1 and 3 can be paired. They can be considered as one MCDC test case. So 1 and 3 can be paired. What is about 1 and 4? It cannot be paired. Why? Because here both A and B value are changing. A2 is changing from true to false, B is changing from true to false. Since both the values are changing, I cannot make it a pair. So 1 and 4 cannot be paired. Now let's see 2 and 3. Similarly, 2 and 3 cannot be paired because here 2 is A is changing from true to false, B is changing from false to true. That cannot be paired. What other can be paired? Let's see 1 and 2. 1 and 2. Here value of A is fixed. That is true. Value of B is changing from what to what? From true to false. Is that in the whole output? Yes. You can see that change. The original result was true, whole result, now it is changed to false. That means this pair true false. That means the value of B, it itself alone, it changes, it affects the whole result, the whole output. So there will be a pair 1 and 2. So you can see for A, test case number 1 and 3 can be paired. For B, test case number 1 and 2 can be paired. So what will be my test, MCDC test case? This 1 union 3 plus 1 union 2, like this. So you can see that first show the independence of A. How you can show the independence of A? By taking row 1 and row 3. Similarly, show the independence of B. How? By taking rows 1 and 2. So that you can say that B is independently affecting the whole outcome. Then what you do? Take the union. So resulting test cases are, what are there? Here 1 and 3, here 1 and 2. So the resulting MCDC test cases are 1 union 2 union 3. What is 1? You can see true true. What is 2? True false. What is 3? FT. So This is the final MCDC test case for the expression A and B. Okay. So how many test cases are there? 3 test cases. True, 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 false, false. Why 2? Because you are having only 2 conditions A, B. So true, true, false, true. In this way, you can design MCDC test cases. You can say that the number of test cases is successfully reduced from 2 square to 2 plus 1. If you could have used normal condition coverage based testing, you have to design 2 square, 4 number of test cases. But if you will design MCDC test cases, it is linear, 2 plus 1, 3. It's a very small example. Let us take a little bit larger example. Now I am taking 3 conditions, A and B or C. So 3 individual conditions we have taken, 3 components I have taken. I want to design this MCDC test case. So if you will design the normal test case, multiple condition coverage test case, how many test cases will require? 2 to the power 3. That means 8 number of test cases will be required. But we have to perform what? MCDC. So in MCDC, what we will perform? What is the first step? Construct the truth table. I have constructed the truth table like this up to this. The result we have shown. Then what is the second step? You find out the pairings for which value of these components that they can independently change the outcome. You can see that one. Let's search for the pairing for A. That means where in the first case A is true, B and C are true, true. Now let's see where A is changing from true, true, false, where B and C are remaining fixed. You can see in test case number 5, value of B and C are fixed, true, true. And value of A is now changing from true to false. What is the net outcome, whole outcome? Yes, there is a change also whole outcome, because initially the outcome was true, now it is changing to false. That means this can be paired. So 5 can be paired with 1 for showing the individual independence of A. Similarly, let's see what about next what we can choose. Let's see 2 into what you can see that it is A is true, B is true, C is false. Now in any other case where B and C values are fixed with the true false, yes, at line number 6, test case number 6, B is true, C is false. That means B and C values are fixed. Value of A is changed from what to what? True to false. So what is the outcome? Is there any change in the outcome? Yes, there is a change in the outcome. The test case number 2 whole output is true, and in test case number 6 the whole outcome is false. When true to false, keeping the values of B, C to this true and false, then the whole outcome is also changing from true and false. That means test case number 2 and test case number 6 can be paired, and that will be one part of the MCDC test case. Okay, so 6 and 2. Similarly, let's come to 3. Again, BC value you can see it is FT, anywhere else FT. Yes, at line number 7 FT is there. That means values of BC are fixed, where and value of A is changing. Yes, in 3 it is true, 7 it is false. What is the net outcome? The whole outcome in 3 it was true, in 7 it is false. That means keeping the values of B and C fixed, by changing the value of A from true to false, there is a change in the outcome from true to false. So I can say that 3 and 7 can be paired. Okay. So similarly, let's go to 4. TFF, and I have to see where it is anything else. Suppose if you see 4 and 8, because BC are fixed, false and false. Here also 8 BC are fixed, false and false. And the value of A is true. Now value of A at 8 is false. But what is the net outcome? In 4, the value of the whole outcome is false. In 8 is also false. That means here the variable A independently does not affect the whole outcome. So 4 and 8 cannot be paired. This is not a valid MCDC test case. But let's see for any other variable 4 and 8 are okay. No. So I have to see then others 4 with, if you can see that if you can see 2, 4 in case of 2, value of A is true. In 4 also it is true. And value of C here is false. It is also false. So only what is changing? Value of B is changing. From what to what? True to false. So let's see the outcome. Yes, in case of 2, outcome was true. In case of 4, A and C are remaining fixed. Value of B is changing from true to false, and there is a change in the whole outcome. It is also changing from true to false. That means 2 and 4 can be paired. The variable B independently changes the outcome, the whole outcome, keeping the values of A and C fixed. That is, A is true, 4 A is true, C is false in 2, C is false in 4, can be paired. You can see no other pairing can happen because the whole outcome is not changing. Similarly for C, only one pair is there, that is 3 and 4. You can look at. So here what will happen? Value of C will be changed. Only A, B will be fixed. See, A is true in 3, B is also true in 4. B is false in 3, B is false in 4. What is changing? Only C. C is changing from true to false. And what is the outcome? Yes, there is a change in the outcome. Here in test case number 3, the whole outcome is true. In test case number 4, the whole outcome is false. So there is a change in the outcome in 3 and what? In 3 and 4. But we are keeping the values of A and B fixed, only changing the value of C from true to false, and the whole outcome is changing from true to false. So now all the pairings we have got for ABC, we have to take the union. So let's see. Let us confirm, find out the union. So note, now we want to determine the minimal set of test cases, and here you can see that there are 2 possibilities. So out of 3, you can see 3 pairs, anyone you take. So one pair you can take might be say 5 and 1. So here 1 5, here 2 4, 3 4. So what do you get? 1 2 3 4 5. Another test you can take 2 6. So 2 6 union 2 4 union 3 4. What you will get? 2 3 4 6. Another pair you can get. You can get this 3 7 3 7 2 4 3 4. So whole if you take the union, what you will get? 2 3 4 7. So since there are 3 pairs in A, I will get here 3 pairs for the MCDC test cases. One is when you take the union 1 2 3 4 5. Another is 2 3 4 6. Another is 2 3 4 7. But we require what? We require the minimal set of test cases. The rule says that if there are n number of components, I have to design n plus 1 number of test cases in MCDC. How many components here? 3 components ABC. As per the rule, I should get how many test cases? MCDC test cases 3 plus 1 4. So here I have got 4 number of test cases. In either case, you see 2 3 4 6 or 2 3 4 7. This is minimal, and this is a non-minimal. This is also MCDC test case. So I can reject this one. Out of these 2 test cases, anyone I can take. So in this way, we have designed the MCDC test cases for a little bit advanced example. Where does it fit in? The MCDC criterion is much stronger than the condition decision coverage criterion, but the number of test cases to achieve the MCDC criterion still varies linearly with the number of conditions n in the decisions, because in MCC it is 2 to the power n, and in the MCDC it is n plus 1. Much more complete coverage than condition decision coverage, so coverage is also more, and at the same time it is not terribly costly in terms of number of test cases. Number of test cases is not growing exponentially. Pictorially I can show like this. The weakest coverage testing is statement coverage. Decision coverage is stronger than this. Condition coverage is also stronger than decision coverage. MCDC is stronger than all these: condition, decision, statement, condition. But this multiple condition MCC, it is the strongest one, because it designs 2 to the power n number of test cases. It is stronger than MCDC, but here we require more time and effort to design 2 to the power n number of test cases. This is the strongest one, MCC. MCDC is the second strongest one, but there is a thorough balance between the test case size and the coverage. With less number of test cases, we are achieving much coverage. So that's why people are using MCDC testing, MCDC coverage testing in industry. Next class we will discuss about the path-based testing. So if you look at the path-based testing, this your first is reach, then all uses use and depth like this. So all uses is stronger than distance coverage, and you can see MCDC coverage is at par with all due paths, and all paths coverage is the strongest testing in case of your path-based testing. Condition second strongest testing, but at the same time it uses less number of test cases and achieves a good coverage, and it achieves a good coverage, thorough coverage while testing software. This is where MCDC test cases, or this is where MCDC testing fits in. Okay, why does it fit in? It like this. It is the second strongest. It fits in at this position. It is the second strongest. It is the second strongest testing criteria. Okay, it is the second. It is the second strongest testing coverage or testing criteria. These are the comparisons of different coverage-based testing strategies. So you can see that that statement coverage only covers every statement in the program. Here, every statement in the program has been invoked at least once. Distance coverage achieves these two things. Like this, you please see. MCC almost covers all, and MCDC is little bit weak than MCC, but achieves almost all the what criteria. So left hand side the weakest, we can say statement coverage the weakest strategy, whereas MCC the strongest what strategy, whereas MCDC coverage testing is the second strongest coverage based testing, or second strongest coverage criteria. We have discussed today white box, several white box testing, white box test case design testing techniques using statement coverage testing, branch coverage testing, condition coverage testing, and MCDC testing. Okay, we have also discussed MC testing technique. Next class we'll discuss MCC. We have already seen MCC. Next class we'll discuss path-based testing. Okay. This we have taken from these two books. Please have a look into yourself. Thank you very much. Any doubt, please? Very important, interesting topic, MCDC testing. Those who are interested to your MTech thesis work or PhD work may choose. So I have already one PhD student have worked in this MCDC testing. Another PhD student is working on. Some BTech and MTech students are working on MCDC testing. There are several tools available. Maybe in the next class I may say. So please have a look into this. Thank you very much. Any questions, please?
Excuse me, sir.
Yes.
Sir, in statement testing.
Yes.
So if a given test case can cover more than one statement, then we do we have to make another test case for those statements?
Not getting what you are saying.
Sir, let's say if a given test case can cover more than one statement within more than one statement in the program, so do we have to make other test cases also for those statements?
No, not required. Your objective is every statement should be covered at least once. If you want one test case covers two statements, then no need to put another one test case for the second one. That I have shown in my first example. I have taken only three, but in branch coverage, you have to explicitly write down test cases, two test cases for each branch. That is most. In statement coverage, if there are 10 statements, but only 5 test cases, you are covering all the statements. No need to write 10 test cases. Okay.
Yes, sir. Yes, sir. That I was asking because in that example, so any value of x and y, while statement will always be checked.
Yes.
So do we have to make another test case saying x is equal to 3 and y is equal to 3?
See, for my example, have I seen my example or not?
Yes, sir. GCD1, right?
That's what I have shown in my while. I have taken only one. And see, in my while test case, just where it is. See, in this example, what we have done here, we have taken only few test cases like this. 3 test cases I have taken. And if I take these 3 test cases, all the statements are executed. I am not taking explicitly once x equal to y, x not equal to y, x greater than y, x not equal to y. So because you see the second test case here, x is greater than y. So since it is already there, in the next case I am not taking. Next case I am taking only for the if statement x is less than y. X is greater than y I have not taken because this is covered here directly. X is already there. But in branched coverage I have to explicitly I am taking for this once x equal to y, then once x not equal to y, then if x greater than y, another is x not greater than y. So 4 test cases I am explicitly taking. Objective is that here all the statements should be executed at least once, and here the objective is all the branches. How many branches? 2 branches, they should be executed at least once. That is the objective. Yes, please.
Okay, sir. So my doubt was about that x equals to y, x double equals to y, y1.
Yes.
So that one, because that while statement could be covered by x not equals to y also.
See, what I have done here, as you are saying, here, what you are saying, see, x is not equal to y, you have considered here. But why don't you also consider the other statement? In one, you are taking x not equal to y, another you are taking x equal to y. But for the second, are you saying here only 2 will be required, or what you are saying?
Yes, sir, only 2 will be required.
No. If only 2 will be required, how you can do so? Suppose you will take these 2 only. X equal to 3, y is equal to 3, x equal to 4, y is equal to 3. Then what is about the if? How you will execute the if then part and the else part? How will execute the then part and else part? One part x must be greater than y, another case x less than y. How will do?
Sir, your PPT is not visible. I am saying whatever I remembered from that slide, sir.
Okay, PPT might not be shared. You just see in while x equal to y, x not equal to y. If you are saying only 2 you can do, if statement cannot be executed. For if statement, I have to again equal to one case x greater than y, x is not equal to y. So 1 you can omit, but it cannot be less than 3. What you do, please you do the homework, please read again today and you ask me in the next class. I am having another meeting now. Okay.
Yes,
you
sir.
Please read it and you ask me again in the next class. Okay. So if there are no more questions, any other questions? Okay, since there are no more questions, I'm stopping. I will put the slide. Please read it today and ask me in the next class if there is any doubt. It cannot be less than 3. Please check yourself. Okay. Okay, thank you very much.